So today we'll start with a topic which is called recursion. Can everyone hear me? Just can somebody confirm?
Yes, sir.
Okay, thanks. So recursion is one topic that makes programming very elegant and it becomes much simpler, but it's a little tricky business because if you make a minor mistake, debugging and doing things could become more complicated than other way out. So I'll discuss a few examples, what recursion means, how do we go about it, and once you see program that looks complicated could be done very simply in a very elegant way. It comes naturally as long as you can define how the recursion works. So as usual, this course says, so no NetAccount is not there, so let me not bother about it. 1 minute, yeah, okay. Let's look at the following problem. 1 minute, I think. Which one had taken slide? Okay, yeah, this is fine. Sorry. So let's look at the problem of you're given n numbers. How do you want to, and you are told to find a sum of n numbers. And these n numbers are given to you in a list. So let's say list is your number 5, 3, 11, -2, 6, 7, let's say 10, whatever. Given this list, how do you find sum of n numbers? So any thoughts? Somebody want to answer? How would you go about finding given normal way? I'm trying to build a case for recursion and how that can happen.
If I iterate through the loop.
Yeah, iterate through a loop. You basically say sum is equal to 0 and then say for element in num s is equal to s plus element, and then you basically say print sum. This is a very simple case and things will work fine. But some problem, things when you touch straightforward and we look at how do you go about it. Let's look at a different problem. Let's say I want to compute factorial n. Same way, you iterate through a loop. For I is equal to, you can say answer is equal to 1, and then I would say for I in range n plus 1, I would say a is equal to a star I, and then I would say print a, and that will give me a factorial. I'm taking a simple case and using this will build the case of recursion, but just trying to do that, how things work out. Finding the largest element of n numbers, same way, take first element as the largest and then compare with every other element. If you find another element larger than this, make larger such that, and then finally print. So these are very simple cases of solving a problem. Now let's look at how recursion happens, and recursion is kind of a natural thing which you see in kind of even real life. Let's look at a tree. If you look at a tree, you look at tree branches starts. And when tree branches starts, so look at here, branches, then each one further branches. So whatever is happening at the root, same thing is happening at the branch, same thing happens at the further branch, and so on and so forth. So if you know how to branch out here, you can use the same logic to branch out here, you can use the same logic to branch out here, and then it should be done. You can look at another probably called Matryoshka dolls, or you normally see a doll within a doll within a doll. So the all doll looks like same, and one couldn't fit into the other. And you see, so one is replica of other. Only thing is the matched doll size becomes smaller. And that's the way. So if you know how to make a smaller doll, if you know how to make a smaller doll, then you can build on top of bigger doll, and so on and so forth. And this is what happens. So typically what it's saying is when you look at a problem, can you look at a given problem into a smaller problem? And if you can solve a smaller problem, then use that solution smaller problem to build a. So let's say you are given a problem and you make a smaller problem. Let's say I've given you some 4 numbers. The problem given to you is sum of 4 numbers, let's say A, B, C, and D. Now, this is a problem of 4 numbers. This is my given problem. If I know how to solve sum of A, B, C, so this is a problem of size 3. My original problem is size 4. This is a problem of size 3. If I can solve the problem of size 3, can I find the solution of my original problem? Anyone? I've given 4 numbers to find a sum. Let's say, and I know how to solve problem of adding 3 numbers. Now, if this addition of 3 numbers ABC is available, let's say this is S. So what would be my final answer? Anyone? No, it's not
D.
C plus D.
SS.
It will be S plus D.
Yes, sir. That's what I did.
Okay. So what I've done is, given a problem of size 4, no, I'm saying 3 elements. ABC is not 3. So I given a problem of size 4, I decrease to a size of 3. Then I decrease to a further size. I go to the smallest size, which is easily solvable. And if I go to only size of 2, I just do a sum and I'm done. And if I get size only 1, that's the answer, and then keep building upon it. And then basically means identify a smaller problem, keep identifying the smallest problem till you can solve by brute force or manually. And once you solve that problem, then keep building upon it. And that is how basically recursion works. It can work as 2 ways. You can find similar problem like this, you limit basically to similar problem, or you can look at a different problem but a smaller size and it's still solved. And I give this example. So today I focus on this, and the next Wednesday I'll further continue with giving a little more defined applications on recursion and see how do we go about it. So essentially we are saying it works where the induction method are used to, so let me not worry about the method, but essentially if I can solve a smaller problem, I do that. Let's say look at my problem, compute n square. So given to me is I need to find n square. And let's say my function fn, and fn is n square. Now, what would be the problem of smaller size? Problem of smaller size would be fn minus 1. So assuming I know how to solve fn minus 1, which would be n minus 1 square. Now, given the n minus 1 square, can I compute n square? So given the solution of fn minus 1, which is a problem of size 1 less than original size n, and I know that somehow there's a black box.
Yes, sir, you can.
So once I go n minus 1 square, so from n minus 1 square, my job is to find n square. What should I do here so that I can get n square?
Minus 2n and plus 1, sir.
No.
No, plus 2n.
2n.
So plus 2n.
Minus 1.
Oh, sorry.
Minus
Sorry.
1, yeah.
Okay. So that means if I can solve a problem of smaller size, then I can add this and get my original answer. and I keep doing it. So for a given size n, I make it n minus 1, then I make it size n minus 2, then make it n minus 3, till I get to size 1. And then I can compute the square, and then keep adding it up, and I get my answer. So let's look at how do we solve this problem. Let's say I need to compute this, and keep doing it, and I'll get my answer. Same we look at factorial n. If I know my factorial n minus 1, if I know this answer, how do I get factorial n? Anuj? Given that I know factorial n minus 1, how do I find factorial n from this?
So you can open n minus 1 factorial, right?
No, so assuming there's something, somehow I got the answer factorial n minus 1. I somehow got that answer. Let him answer whenever. Let's assume I know the answer of factorial n minus 1. Can I compute factorial n from this answer?
Yes.
How?
Yes, sir.
Yeah, Anuj, let him
Multiply.
answer.
Multiply.
So by adding 1.
Not add 1.
No, it's factorial. How can you add 1?
So what should I do? See, if I were to multiply this by n, will it give me the answer?
Yes, sir.
So if I can find the solution to factorial n minus 1, I use that solution, multiply by n, and that gives me factorial n. Okay? And I keep doing it, and n minus 1 becomes n minus 2, n minus 3, till I becomes 1, and I know factorial 1 is 1. And then I keep building it up. So this is what I keep doing it up. You know what GCD is? Highest common factor. Let's say I want to find highest common factor of 20 and 12. We know that GCD of 20, 12 is same as GCD of 12, remainder, which is 8, which is same as GCD of 8, 4, which is equal to 4. Does everyone agree with that? This is how we do GCD? Abhiraj?
So what is GCD?
Greatest common divisor or highest common factor.
Yes, sir. Okay, yeah.
You can keep taking a remainder and keep doing it till you find the answer.
I got what.
So that means I can find GCD of y, x if I can find GCD of x, r, where r is remainder of this. Okay.
Yes, sir.
So this is the way, using this property, let's see how we can find our solutions. So primarily we're saying in recursion, given the problem of size n, decrease into a smaller problem some factor. It could be n minus 1, it could be n by 2, it could be something else. And I give you a few examples and solve that problem. And using that solution, when you solve the smaller problem, use this solution of a smaller problem to build my actual solution. And that is basically what recursion is. So primarily 3 parts. One is first, break the problem to smaller part. Second, solve the smaller part by brute force by some way. And then combine the solution. And that's what we'll do when doing a recursion. So let's look at how do we go about doing it. You see this all across: reverse, trees, dolls, art patterns, name it. And the beauty is when you can understand recursion, your program become elegant, very small, simple to follow. though it may be little more time consuming, but at the moment, we're not going to worry about that part. So essentially, we are saying, keep reducing the problem till it becomes a very small, which you can solve. You know how to solve that smaller problem, and I give the example there. Only challenge is you should understand how to break the smaller problem and how to solve it, and then continue. So I'll give a few examples there. Come to that. Let's look at recursive sum. So assuming I have a given function n, my job is to find sum of 1 plus 2 plus 3 plus 4 up to n, or you can say I given a number in an array, which is array is a, and some number is given a1, a2, a3, and let's say an. And how do I go about finding the sum? So I'm saying if my array size is, look, if my array size is 1, I know my answer is the element itself. This is what is called a brute force, because I cannot make a smaller problem than size 1. So if my array size is 1, I get the answer. If array size is not 1, that means more than 1,
You'll use elif.
then you use the answer. I would say nth element plus sum of first n minus 1 element. So if I take the sum of first n minus 1 elements using the same function, I'm using the same function here. Look, this is the same function. I'm calling myself. This is called recursion. Using the same function, I'm asking to solve first n minus 1 elements. Once I get the answer, I add this nth element, and that gives me the answer. So basically, I keep using same function again and again till my function becomes so small that I can do manually or brute force and work upon it. So let me give the example there. Let's say, consider the following array elements. Let's A is this, which is n is equal to 5. I need to find sum of 5 elements. So sum 5 would be fifth element, which is 9. So 9 comes here. Plus sum of 4. Now sum of 4 means I'll take 9. I'll define sum of 4 is I take fifth element plus sum of 3. So this becomes 9 plus 5 comes here and sum of 3. I'll keep doing it till I get sum of 1. So the sum of 3 would be this third element here plus sum of 2. So you get 9, 5 and 17 comes here plus sum of 2. Then further 9, 5, 17, sum of 2 is 8, and then you get 11 because sum of 1 I know is a1, and then I keep adding it, and that gives me the answer. My answer is 50. So once I know the solution to a smaller problem, I can find the bigger problem. So this way, I'm not writing a loop. So remember, key part is I'm calling the same function with a smaller size problem till I get the problem to be small enough. It could be n is equal to 1, it could be n is equal to 2, depending on what my problem is. So typically 1, 2, 0, I solve it by brute force. So in recursion, this condition of solving by brute force is very, very important, because if you miss it, the program will go for it all. So never miss this part. And then you understand everything, what is being done. Is everyone clear about this example, or any doubts? Or do I need to repeat here?
So what does A of n imply over here?
Nth element. I'm assuming the index is 1 to n. You can say n minus 1, that should be fine. I'm not worried
So
about
but
yeah.
won't it throw an error if we haven't defined
In Python, it will give me error. So it should be n minus 1. I'm looking at the logic.
Okay.
Nth
Yeah,
element. Assuming indexing starts from 1.
Okay.
I'm writing a normal logic. Ideally, it should be 0. So if you really want it, the program should look like the following. So rather than A1, it should be A0,
Yeah.
and this would become A n minus 1 plus sum n minus 1. This is the right program. Is that okay?
Yes.
Yeah. So I'm looking at more of a logic rather than anything else.
No, sir, that'll remain A of n only, right? Why will it be A of n plus
No,
sum
A of
of
n
n
in
minus 1?
Python, last element is n minus 1 index. If
Yeah,
size of
right.
5, it will be only A4.
Yeah.
Okay, it cannot be A5.
Okay, yeah, correct. Yeah.
Fine.
So,
Any question? Krishna, Shreyas?
No, sir.
Yeah. Any question about this? Has everyone understood? Shreyas, is this fine?
Yes, sir.
Krishna, is it fine?
Yes, sir.
Okay. Let's go to the next problem. Computing square. I want to find n square. Now, if n is equal to 1, my answer is 1. Correct?
yes,
If
sir.
n is not 1, then we know the answer is square of n minus 1 plus 2n minus 1. And this gives you the answer. I'm not writing any loop at all. I'm calling the same function square with a smaller size than this was. This is reducing my problem size. So my original problem of n has become my problem of n minus 1. It will call further itself with n minus 2, which will call further itself with n minus 3 till it becomes 1, and then I get the answer, and then keep building it. Let's look at the example here. Let's say I need to compute the square of 5. The square of 5 means n is equal to 5. So this condition will fail. So this condition would fail. That means I'll come to this. So it will be 2 into 5 minus 1, which is 9. 9 plus square of 4. When n is equal to 4, this condition fails. I'll come to else part. So that means square 4 is 2 into 4 minus 1, which is 7, plus square of 3. So this becomes 9 plus 2 star n minus 1. So 2 into 4 minus 1 is how much, Abhiram? It should be 7, not
7.
6. Yeah. Okay. So 9 plus 7 is square 3. When I come to square 3, n is 3. This will fail. So this one, this becomes 2 star 3 minus 1, which is 5, plus square of 2. So 9, so and so. And then it is 3 plus the square of 1. Now n is equal to 1. So square 1 gives me 1. So my answer becomes 9 plus 7 plus 5 plus 3 plus 1. Keep adding it, and you finally get answer as 25. I got the square. There is no loop there. So essentially, I'm using the same function with a smaller size problem to solve. And that is what the beauty is. It becomes very simple program. I'll tell you further examples there. Let's look at the permutation. You know what NPR is? Factorial n upon factorial n minus r. Is anyone not aware of it? Anuj, is this definition fine?
Yes, sir, it's fine.
Fine. Let's say how do we solve it? Now look here. When I permute n is comma r, we assume, is assumed implied that n is greater than or equal to r. N cannot be less than r. Okay? We are assuming that. So if somebody calls it, it should always be n greater than or equal to r. No, so that's a check we are saying. So how do you define? So and we know that. So what is if, let's say, I need to say 5 P3 would be 5 into 4 into 3. This is what we are looking at. That means I should get basically all terms. And then I should stop. So 5P1 would be just 5. One term. So whatever you get number here, you get that many terms, multiplication keep decreasing. So let's look at how does my recursion looks like. So I would say if n is equal to r, that means I had done with all the terms, then return n, the last element, whatever this thing. Otherwise, return n star permutation of n minus 1 r. It may be a little confusing, but let me give example with you. Let's say I need to compute permutation 5, 3. No, let's look at it. Look at the example there. Let's say we need to compute 5, permutation 5, 3. So we know 5, 3 is 5 star 4 star 3. That's how does it work? Now when I call 5, 3, n is my 5 and r is my 3. That means this condition fails. So I need to return 5 star permutation 4, 3. So I return 5 star permutation 4, 3. I come back to it again. N is 4, R is 3. So this condition fails again. I come here. Now N is 4. So permutation 4, 3 would be 4 star permutation 3, 3. Yeah. So let me come to it, okay? So let me come to it here first. Now, so this will become 5 star 4 star permutation 3, 3. And we are saying here, now n is 3, r is 3. If both are same, return n itself. So that means permutation 3, 3 return 3. So my answer becomes 5 star 4 star 3, which is 60, and I get my answer. Any questions about this? Anyone? Shreyas? Is this confusing?
No, sir. It's clear.
Krishna?
Clear, sir.
Look, I am not doing any factorial anywhere. It is automatically implied. And you get the answer. Very simple code. There's no looping, no counting, but just done. Anuj, are you fine? Abraham, is that okay now?
Yes, sir, I'm fine, sir.
Abraham, fine. Now let's look at another example. Finding a maximum element. Given an array, find the maximum element. Now how do I write the program? So input is an array, whatever it is. If my length of array is 1, if array is only one element, that's the maximum. That's the minimum as well. But if it is not 1, more than 1, then what should I do? Find the maximum of first n minus 1 element, whatever that max is, and compare this max with the nth element. So if max is greater than nth element, return max, else return an. So essentially what I'm doing, my given problem of size n, I reduce to size of n minus 1. And once I get the answer, using this answer, I'm finding my max. So key part is this terminating condition is very, very important. If you make a mistake here, whole thing will backfire. Nothing would work. But once you know the identifying condition, the terminating condition, life becomes very good. The program becomes much simpler. So let me not worry about. Let's look at Tower of Hanoi. How many know about this problem, Tower of Hanoi?
Sir, in the
Previous case?
sir, I have a doubt.
Let me go to previous case. Yeah, tell me.
After the else block, max equal to find max. Shouldn't you slice the array every time you call the function?
I'm giving an index, so it doesn't really matter.
Okay, you're slicing from behind. Okay, got it.
So doesn't I can start from behind, doesn't really matter. Yeah.
Got it.
Okay. It's the way how to implement. I'm giving a logic.
Okay.
Is that fine now?
Yeah.
Anybody have any question about it? And I'm teaching recursion because I have seen not many people understand recursion. And if you can know how to use recursion, your programming will go a level above than everybody else. It's a very beautiful concept. And sometimes I'll give an example and say how can it be done? And then you see answer comes very quickly. Is there anyone who knows this, doesn't know the problem of Tower of Hanoi? Abhiraj,
Sir, I
you know
don't
the
know.
problem?
I don't know. No, sir.
So who else doesn't know the problem of Tower of Hanoi?
Sir, even I don't know.
I don't know, sir.
We don't know. Okay. So let me give you the origin story. It seems that, I don't know true or false, but what the origin is that there are a monk sitting in a Korea somewhere in the hill, and there are 3 towers, and on these towers they have what is called 64 discs. Like in this you see 5 discs, and they need to move all these discs, all these 64 discs from tower A to tower B using tower C as an intermediate. The only condition is you can move only 1 disk at a time. You cannot take 2 disks. You can move 1 disk at a time. And secondly, you cannot put a larger size disk on top of a smaller disk. So like I can move this purple color disk here, then I can move this yellow color disk here. So let me clean this up. So let's say I can move this purple color disk here. Asking Ugram, tell me. Meaning? We will do that. Okay, let me explain. Then I can move the yellow color disk maybe here, because I cannot move yellow color disk larger than purple, so yellow color disk cannot come here. Just 1 minute. Hello Rekha. I'm in a community class, so can I call you back? No, sir, can I call you? I'm in another class, Rekha. I'm doing a community class. No. Sure. Yeah. No, Rekha, I'll call you. I'm in a class right now. I'll call you. I'm in a class right now. I'll call you back. Yeah. Sorry, guys. It was called from my college, so couldn't avoid. Okay. So I cannot move this yellow disk on top of purple disk because bigger size. So my condition is, so now I can do is, so this I cannot move. Now what I do, I can move this smaller disk purple on top of this disk. So see, I moved the two disks. And then I can keep moving this blue color disk here. Now this has become empty. I can move the blue color disk here and then keep moving. The problem is I have to move all these 5 disks onto tower B. I can use tower C's empty tower. With the condition is I can move only one disk at a time. And second condition is I cannot place a larger size disk on top of a smaller size disk. How do we solve that problem? This is problems called Tower of Hanoi. It's a very well-defined nested problem. And the incident and story is, if this what they say is original in the Korea, the total number of disks are 64. There are monks who keep moving the disk, and they say the moment they move all the 64 disks onto tower B, world will come to an end. That's the anecdote. But this will take too much time, and don't worry, it will be another few million years before this could happen. So don't worry about that part, but that's what the problem is. Is the problem clear to everyone?
Yes, sir.
So how do we do that? Let's look at how can you apply recursion. Assuming now I have a 5 disk here. Assuming I don't have the bottom disk. Instead of 5 disks, I look at the problem of 4 disks. I know I have to move 5 disks, but I look at the problem of 4 disks, and I move this 4 disks onto tower B using tower C. Now once I move this 4 disks, I move this 4 disks onto tower C using tower B as empty tower. Once the 4 disks are moved, then I move this green disk here, tower B. Now I have back to same problem of size n-1. I move back n-1 to this using A as empty tower. So essentially, if we look at Tower of Hanoi, of the problem of size n, I reduce to problem of size n-1. I first move this n-1 disk onto tower B. Then I move one disk green onto tower B, which is I can move. And then I move remaining n-1 disk back here. So I first move n-1 disk, then I move one disk, and then I move n-1 disk again. And this is what, so let's say how do we go about it? Yeah.
So you keep moving the disk from A to B
No, my
and A to
objective
C, then
is-
C to B.
My objective is I need to move this 5 disk onto tower B, following my rules. Rules are one disk at a time, and I cannot place a higher disk on the smaller disk. As I showed you, let's say if I had only 2 disks to move, I had 2 disks to move, assuming there are only 2 disks and not the 5 disks. If only 2 disks to move, how would I move?
You would move
So first I
purple one
move,
to B.
I need to move both of them to tower B. So what I'll do is I'll move this purple color disk to tower C. Then I move this yellow color disk to tower B. And then I move this purple color disk on top of it. So this is my yellow disk, and this is my purple disk, and this comes here. Okay, I moved. So from size of 2, I made it size 1, and I'm done. Any questions? Is the problem clear?
So could you just repeat again?
Let's say I have only 2 disks to move, not the 5 disks. And I need to move this
Okay.
2 disks onto tower B using my rules of the game. And rules of the game is I can move 1 disk at a time. And second is I cannot place a larger disk on a smaller disk on top of it. So how to move these 2 disks? I need to move them to tower B. So first I take this purple color disk, smaller disk, move onto tower C. Okay.
So could you move it to tower B?
And okay, if I move to tower B, what would happen? Let's say, good question. If I move this to tower B, then what should I do next?
So move the orange block to tower C.
I move this yellow or orange to tower C. Then what should I do next?
Take the purple to C.
Purple to C, yeah.
Which one? The purple to C. Okay. When it goes here, did I move this 2 disks to tower B or to tower C? What I wanted to move to tower B. Remember, this was the objective. But I ended up moving to tower C. I had asked you to go to classroom number B, but you ended up going to classroom number C. Got it?
Yes, sir.
Yes, sir.
Fine. That's why you need to move other way out. Okay. So let's say given the problem of 2 are done, so assuming I have a disk of n disk, assuming I don't have the bottommost disk. Remember, once this bottommost disk moves, this doesn't really matter, I can solve the problem. So if I can solve the problem of n minus 1 disk, if I can solve it using my logic, so what I need to do, I move this n minus 1 disk to tower C, then I move this green disk to tower B, and this is, see, my original problem was size n, I made it size n minus 1, and this is size n minus 1, and then I move n minus 1 back here, and I'm done. Okay. Spend time on it, then you get to know, think about it. It may take you a while. So graphically, you can look at the following. So I move the n minus 1 disk here. Then I move bottom disk there. Remember, my original problem was moving 5 disks. I made a smaller problem of size 4. So I'm solving the problem of size 5 by solving the problem of size 4. If I can solve this problem of size 4, then I can move 1 disk, then move the remaining 4 disks back here, and I got the original problem solved. How to solve the problem of size 4? Make it a size 3, make it a size 2, make it a size 1, and keep doing it. And that is how.
So how can you remove the lowermost disk?
No, I'm not doing lower. Where I'm doing lowermost. See, this is the heavy disk. Once it is moved, forget about it, because everything can come top of it. This doesn't have to move. The lowermost disk is the heaviest. Once it moves, it doesn't have to move again. Okay, anything can come top of it. It is not going to move on top of it. So let me repeat.
Yes, sir. Yes, sir.
So I'm assuming this is my size of problem 5. I reduced to problem of size 4. Assuming my program can solve size 4. How do I solve size 4? Move this 4 disk to tower C using the same program using B as the empty tower. If problem can solve a size 4, I can solve size 5, I can solve a size 4. So this, I move using same problem, smaller size to size 4. Now only one disk left, tower B is empty, and this disk can go there. Okay, I'm doing one disk at a time. And now my problem is size 4. Using A as the empty tower, I can move this 4 disk on it because these are all smaller than this disk, so they can be all be moved. This doesn't make an impact. And this is what I do. Okay.
So, but how are you moving all the disks
I'm not
together?
moving. Same problem. So whatever my program was, let's say my problem was tower 5. It is doing something. I'm doing it using tower 4. I'm making it of size 4. Tower 4 will become tower 3. Or let me say, let's say my program is called TH of 5. Okay. This is my program. Def TH of 5. So let's say my program is def TH of 5. Okay. And what I need to do is TH of 5 move from A to B using C. Correct? This is my problem. Are we okay with it? I'm defining the problem. What I can do is I can say use TH, same itself, using size of 4, move from A to C using B. I'm using the same program. But what is my terminating condition here if you look at? So let me say this is my N. If N is equal to 1, move A to B. One disk, this physical move. I don't need to call this function. If N is not 1, then I need to do my work. So this is my terminating condition. If N is 1, move one disk from A to B. That I can move physically. If N is more than 1, then what I need to do? Use TH. I don't have a space, so I'll erase this. Remember terminating condition. If N is not 1, then I say use TH, move N minus 1 disk from A to C using B. Once N minus 1 disk has been moved, I'm left with another disk at the bottom. Then I would say move bottom disk from A to B. And now I'll say TH again, N minus 1 disk. They were on basically tower C. Let's say move from tower C to tower B using A as the empty tower. And that's how my program will look like. I'm done. This will just work. It will keep calling itself and get the answer. So spend your time, Google it out, look at the program's available. And if you don't understand it, we can discuss again in the next class. Okay?
Sir, I have a doubt.
Yeah.
The last line,
Yeah.
you move N minus 1 disks from C to B or C to A?
Look, originally what is my problem? Move N disk from A to B using C. Is this problem clear?
Yeah.
So I'm saying move N minus 1 disk from A to C using B. That means at this point, my top n minus 1 disk
Okay.
are at C. After this is
Okay.
done,
Got it.
I have to move from C to B and A is empty now. Got it?
Yeah.
So again, spend time, logically look at it. There are enough programs in Google, search it out, you understand. And beauty of recursion is just 3 lines of code solve the problem. Very elegant. No more work. So if you look at Google, you get a 4-line answer. Answer is there will be one print statement here. There will be one print statement here. Print which move, so that you know what has happened. Okay. So let us not worry about this part. We'll get into complexity part. So essentially, let's look at. We are saying, I need to find sum of first n numbers. Give another very recursive approach. So that means 1, 2, 3, 4, 5, 6, 7, 8, whatever. Non-recursive approach is this is size n and this is n plus 1. If you look at the two diagrams are symmetric. So if I take n into n plus 1, that gives me total number of squares. And the two diagrams symmetric, I divide by 2 and I get the answer. This is a non-recursive approach. Are we okay here? No. 1 to n would be n into n plus 1 by 2.
Yes, sir.
So could you explain why
Sir,
you divide by 2?
Sir, I didn't get the question itself.
Question is, I need to find 1 plus 2 plus 3 plus up to n. Okay, I need to find this answer.
Okay, sir.
Okay, how do you find? So I'm depicting by graphically. So this is 1 is small square, 2 is small square, 3 small square, 4 small square, and let's say I get n small square. So if I count the total number of squares, I'll get my answer. Aruna, is that fine?
Yes, sir. Yes, sir.
Anybody else? Is that out? Tell me, Abraham, what is the question? No. I'm saying n. Look at it. Okay. So I need to count n, 1 plus 2 plus 1 plus 2 plus 3 plus 4 up to plus n. Okay. So this is 1. This is 2 squares. This is 3 squares. And this is n squares. Is that okay, Abhiram? If I count the total number of squares, that will give me the answer of the sum. Now, can I make it complete rectangle? I make a mirror image and put on it. So it becomes a rectangle of this side is n and this side is n plus 1. So what is the number of squares in this rectangle? N into n plus 1. And I have two such figures. I wanted only one figure. That means number of square in one figure would be by half. Okay. Any questions about this part? Anyone? Krishna?
No, sir. Clear.
Clear? This is non-recursive approach. I'm telling how to solve by recursion. Now let's do this. I'm done. So let's look at this non-recursive approach. Let's look at recursive approach. To find the sum of n numbers, one is if I can find the sum of n minus 1, then add n to it, I'll get my answer. So I can say Sn is nothing but n plus s of n minus 1, where s1 is equal to 1. So my program will look like, if I were to write sum n if n is equal to 1, return 1, else return n plus sum of n minus 1. Are we okay? Anyone has a doubt about it? I'm avoiding any looping here. Look at, so there's no boundary conditions here. Only this is important. Abhiraj, will this work?
Yes, sir. Yeah.
Yeah.
It
Okay.
will.
Now, so this is one approach using recursion. Look at another approach. So this you can probably leave it away. Let's look at it differently. I made it same figure of 3 different kinds. If this is n, look at n is given, let's say in this case n is 8. So I make a problem of size 4. This is the problem of size 4 again. This is the problem of size 4. And this is the problem of size 3. So if I can find the answer of size 4, size 4, size 4 and size 3, I'll get my answer. Because it's the same problem. I have a bigger diagram, I have a smaller diagrams. Okay. If n is odd, so look at, my answer would be if n is even, I get 3 smaller problem of size n by 2 and 1 smaller problem of n minus 1 by 2. So 3 problems of size n by 2 and 1 problem of size n by 2 minus 1. And this will give me the answer. This is when n is even. What happens if n is odd? If n is odd, I can do same thing. I'll get 3 problems, let's say this n is 7. In this case, you can look at. So I get 3 problems of size 3 and 1 problem of size 4. That means n is odd. So I'll get 3 problems of n minus 1 by 2 and 1 problem of size. So these 3 problems. And 1 problem of size n plus 1 by 2. This is 1 problem. So my answer would become 3 problems of n minus 1 by 2 plus 1 problem size n plus 1 by 2. No, so I'm doing recursion. So using S, I'm solving half a problem and doing that. So that's what I'm basically doing, talking about it. If n is 1, answer is 1. If n is 2, answer is this. Otherwise, use this formula, write the equation to get the answer. This is deliberately given complicatedly to give you how recursion could be done, but you don't do for this case. But other cases you can do much better. So let me come to basic simple recursive code here. So code for sum of n, this is my code for this program. This will give you sum of first n numbers. Look, there's no looping anywhere. The same function is being called at half the size of the problem. Not n minus 1, half the size. And when we do what is called binary search, in next class, we'll use this mechanism of dividing problem into half. Okay? We'll look at that. That I'll do next class.
So, sir, what we did right now was dividing this problem into half, right?
Right, yeah. This problem into half.
Instead of using LF again and again, we just directly use the if and else
No,
function.
I need to have terminating condition because some point recursion has to stop. I cannot keep calling it. So this is my terminating. Remember, in recursion, these terminating conditions are very, very important.
Yeah.
Unless you do that, program will go for a toss. So what is the smallest size problem you can solve yourself directly? And then build bigger problem on top of that. That's the key point. Okay? Is that okay? We'll do that in the next class. You look at that part. So we basically look at recursion, take the given problem, make a smaller problem, sorry, typo error there. Find the smallest problem which you can solve, use that solution to get actual solution. Now using that approach, you should basically compute, you know what NCR is? Combination. You know what NCR is? Is equal to factorial n.
Yes, sir. N
upon
factorial by n minus r factorial.
Into n minus r factorial.
Minus r factorial.
This is a formula for NCR. But you compute 3 factorials. I'm saying using this recursion, I can solve the problem. So given problem of size n, so n is always greater than equal to r. We are assuming that. So if what I need to do, a given problem I made into 2 problems, one of size n minus 1 and size r minus 1, other is size of n minus 1 and r. And then I can solve it. And remember NC, not NC1, sorry, NC0, my mistake here. This is NC0. NC0 is equal to 1 and NCN is equal to 1. So if we look at how the answer will look like, you try it yourself. Beautiful way doing that. Let's say my function combination n comma r. I would say if n is equal to r or r is equal to 0, return 1. So let's say combination n comma r. If n is equal to r or r is equal to 0, return 1. And this is, I said 0. Okay. I've returned 1 or return 1 here. Else, I say combination of this n minus 1 comma r minus 1 plus, sorry, return, else return, sorry, let me correct it. Return combination n minus 1 comma r minus 1 plus combination n minus 1 comma r, and we'll get the answer. Simple NCR, this program would give the answer. It looks surprising, but you'll get the answer. There's no factorial business anywhere. It happens automatically. because I could define problem into a smaller size. Okay? Any questions about this? Write a program and do that, you'll get to know. Anuj,
Yes, sir.
is that fine?
Yes, sir, it's fine.
Let's look at the next problem. Find the maximum number. First, you do the solve loop, decrease by 1, and then you make into 2 halves, and then solve 2 parts. I expect you to solve the first part. Second, I may not expect you to solve, but if you can do great, at least do by this. So given an array A, find the max element. We'll talk about that. Try doing the first part at least. Using recursion, try to solve it. Third exercise is, you know what Fibonacci number is? 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 57, 55, and so on. Basically, take the last 2 numbers, sum them up, you get third number. Take the last 2 numbers, sum them up, take last 2 numbers, sum them up, take last 2 numbers, sum them up, and that's what the Fibonacci number is. Okay? So program would be simple. If the program would be, if n is equal to 0, return 0, else if n is equal to 1, return 1, else return this, and it will be done. You can look at that. Again, compute power of n raised to power k, which is n star up to k times using recursion. You can solve it by n star into nk minus 1. And when k is 1, you know the answer. So this is my terminating step. Second is a look at, or you can say k is equal to 1, return n. Either way is fine. Both are fine. Other is, I make it, remember, n ki power k, n power k is equal to n ki power k by 2 star n ki power k by 2. So I can make a problem with size half, multiply them, you'll get the answer. But this works when k is even. If k is odd, then you do k minus 1 by 2, k minus 1 by 2 into n. Using a recursion, you can solve power of n. I mean n power k. So these are the exercises I would like you to do. Spend your time, discuss the answers on the group, sell them, ask questions, try to learn, do it, and Google it out, Hanoi style. If you still have to tell me, then I'll show you the program. Any questions?
No, sir.
How many people try to do the exercise I given you previously, the game? What is the game? Tic-tac-toe. How many people?
Still working on it.
Discuss, build a game. It may be an interesting game to learn, define the programming. Okay, that will tell you how to programs to be written. Okay?
Yes, sir.
So anybody can build solutions, give it to me so that I can look at it and tell you what mistakes. Then only when you write, then you learn how to do that. It's an interesting game. And then do the recursion. So next class will be on Wednesday, same time. Fine?
Yes, sir.
Okay, thank you guys.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank